It's a great honor for me to be celebrating Jim. I heard about Jim Simons, as a mathematician before knowing about all this has done for mathematics as a supporter. So I was an undergrad when I first encountered some of his mathematical results. It's not about Chen Simons. He's always remembered for Chen Simons, but he did other stuff which has been very impressive, and I will mention that. So I first heard the name as a mathematician, then I moved to US. I was a faculty for 7 years in the US, and I had the chance of learning about all the great things that the Simons Foundation was doing for mathematics. And I first met Jim then slightly after, in 2019. And I remember I was at dinner at his place. There were many people. And of course, he was trying to get, wealthy people to support research. And I was very impressed by his way of doing it, because we had this dinner. We were all sitting. I was next to him. And then he just said, I'm raising money for what is called now SLMAT, former MSRI, so Research Center in Berkeley. And he said, so before you leave after this dinner, please write a check for $100,000. And that's how we're going to raise money for MSRI. And then I kind of froze. And I was like, does it mean I have to write a check for $100,000? I felt, and then he looked at me immediately and said, you're a mathematician, don't worry. You don't have to. I'm not asking money from you. I say, thank you. I forgot my wallet, So I would like to talk a bit about topics of mathematics that influence my research, and this will be also a way to talk about something that Jim did. So I will start with a connection, how you can go from soap films to ice melting. Some years ago, there was an article in Quanta magazine, which is also supported by Simons Foundation, which is a beautiful journal. There are many articles on every kind of research, especially mathematics, physics, and it was about studying the melting of ice in water. So this is something I did in the last years. And it has been a project that has been very fascinating. And is actually something that looks very easy. I don't know if the video, okay, yeah, the video will start. It looks like a phenomenon that should be very easy to describe, but in reality, when ice melts in water, there are many subtle things that can happen. The ice can break into multiple pieces, and really modeling this, such a simple phenomenon, actually is extremely complicated. So the way we do it is through a model that has been proposed by Stefan in 1890. And essentially, you just have a container, you have some ice inside the water, and you just want to understand how this ice evolves in time. But you see, there are, let's see, if I understand how this, this point, okay. You see, there are points here where the ice is very thin, and these will be points where the ice will break. And these points is what are difficult to capture and understand. So the challenge is exactly that. The interface may develop singularities, and the question is, how can we study them? So there have been a lot of progress, but at some moment, mathematicians got stuck. Like, they couldn't really analyze properly these singularities. And sometimes, when you lack ideas, you may want to look somewhere else. And in our case, the connection came from another topic, which is called the plateau problem, which is about soap films. So soap films, like soap bubbles, take certain shapes just because they minimize some energy, which is the surface area. And more than 200 years ago, Plateau asked, what is the least area surface spanning a wire loop? So you see that there are a lot of simulations. It's very easy to build these examples. And this kind of study led to a mathematical theory, which is called the theory of minimal surfaces. And that's where Jim played a crucial role in the 60s. So let me give you an example. So if I tell you that I have two dots, you see there are two dots on the top and two dots on the bottom. And I ask you, what's the best way to connect them The answer is very easy. You just draw two segments connecting them. That's the best way to connect the two dots on the top to the one at the bottom. So this is what will be, so we are in a planar situation, so we are in 2 dimensions. And these two segments are what we will call a minimal surface, because it has minimal area, in 2 dimensions. So the 2 dimensions is because we are in the plane. Now, if you do the same experiment in 3 dimensions, the analog will be to connect a circle on the top to a circle on the bottom. And the way you do it is through a 2-dimensional surface, that is the one that you see in this drawing. And what you may notice is that while in 2 dimensions, the minimal surface is 2 straight segments, in 3 dimensions it's not a cylinder. Instead, the surface tends to bend like this. You see, it tends to get kind of shorter in the middle. And then mathematicians kind of ask themselves, okay, what happens? So there is a change from 2 to 3 dimensions. What happens if I go to dimension 4, 5, 6, 7, 8? I don't know. So there has been work by Bernstein, De Giorgi, and then Jim between the 50s and the 60s. And this was a major result by Jim that proved that up to dimension 7, you will still see the same picture. Nothing changes. So there is this beautiful paper in 1968 where he proved exactly that result. And in that paper, he wrote, I didn't manage to ask him properly this question, but I think he was kind of frustrated because he could only prove this up to dimension 7. He was stuck and said, oh, I cannot do that in dimension 8. So frustrating. And then he said, well, actually, in dimension 8, I have an enemy, something I don't know how to prove that it doesn't do that. And that's what he did. In 1968, he wrote this example. So there is a formula. How do you write a surface in 8 dimensions? I don't know how to draw that, but you can just write with coordinates. You know, points in 3 dimensions have coordinates, x, y, z. And if you're in 8 dimensions, you will have x1, x2, x3, x4, and so on. And he wrote that formula. It's a cone, it's a surface in dimension 8. So there are 8 variables. I draw it in this way. And it turned out in 1969, it has been proved that the Simon's cone is a minimal cone, which means there is a singularity. So in fact, his theorem was the best he could prove, because in dimension 8, minimal surfaces are not smooth. They create these kind of singularities. And so this is called the Simon's cone, which has inspired then all the work in minimal surfaces from the 60s onward, because we realized that minimal surfaces are not smooth anymore from dimension 8 and higher. So there is a change in that. So this was Jim's milestone. Singularities are unavoidable. And this is linked to other theorems, like the positive mass theorem. I mean, this is really connected to a lot of physics and development in mathematics. So this is about, so all the work that people did, like Jim and previous mathematicians, were mostly interested in surfaces that are like always 1 dimension less than the space. So let me just go back, like here you see it. I'm in dimension 2, I'm considering lines. I'm in dimension 3, I'm considering curves. If I go to dimension 4, I will consider 3-dimensional objects. So they were always looking at objects which were only 1 dimension less than the ambient space. But there is no reason for doing that. You could say, what if I take a surface, a 2-dimensional surface, but I look at it in higher dimension, like in 4 dimension. So you kind of look at, there is no reason not to do that. And that's what Almgren, who was in Princeton for many years, looked at. He started to look at soap films in 4 dimensions. And essentially, okay, again, I cannot draw that properly, but the problem is that once you have extra dimension, you have space to wiggle around, because you have like a curve. I mean, a curve in the plane cannot do much, but a curve in 3 dimensions has much more space to go around. The same way a surface in 4 dimensions has more space to go around, and it creates new singularities. And Almgren wrote this book. In fact, he didn't write it. He wrote it unwritten, and then he passed away. So his former wife wrote it. It's more than 1,000 pages book, where he kind of studied exactly this problem. And he develops a lot of beautiful mathematics there. And then it turned out that the mathematics that Almgren studied and developed there is exactly what we needed to study this problem of ice. Essentially, Algren found singularities that we found again in the ice breaking problem. It took us 40 years to realize that. And so this was really the new roadmap to tackle some open questions that have been open for many years. So that's what the Rowing mentioned in his articles, mathematicians prove melting ice stays smooth. Essentially what we could prove, thanks to these insights from soap films, was that first of all, the ice actually stays smooth almost all the time. So these singularities that appear, but they very rare, only exceptional. And when they appear, that's, I think, the key point that people were missing. Actually, there is regularity even in the singularities. So they cannot just break in a totally crazy fashion. If they break, they kind of arrange themselves in a very regular fashion. So there is regularity in the way they break the ice. So there could be a lot of singularities, but they cannot just happen like in a fractals way. Actually, fractals don't appear in ice breaking. That's the kind of message that we could understand. So this was actually an example of a word by Wigner when he said a reasonable effect of mathematics. So the fact that sometimes mathematical concepts from different areas can really inspire other areas where there is a priori no connection. So here in our case, we had this model which was very old, 130 years old. And it is only because mathematicians worked for so many years on soap films that we could kind of then advance that model on ice breaking. And there is no way to do that except you just let the people have time to think about problems and try and error, failure, and sometimes likely success. So this is this kind of problems in phase transition and ice melting is just part of a big branch of mathematics which is called free boundaries. And this is really a topic which is very exciting, and there are really many areas. So just to mention a few examples, also to inspire why there is a lot of research going on in these topics. A classical example of free boundary happens in finance. So when you have American options, for instance, you have to decide when you exercise your options. So there is a moment where you want to exercise so that you get the best possible reward. And this is a sort of, is again a free boundary problem because in some sense you have to understand at which moment it's worth to execute the option or not. And so yeah, there you see a graph of the SP 500, which now is way higher, but and this is just the exercise region, so it tells you at which moment you want to execute your option. So that's an example. In physics, let's say that you have charged particles, and there is some potential, external potential that pushes them and confines them. They will usually organize themselves in some shape, and usually you don't know exactly the shape, but you try to understand what are the possibilities for this. So usually you have some confining potential, you have some energy of interaction between particles, Newtonian or whatever, and the question is, what can you say about the boundary of these clouds that they form? So there are a very exciting phenomena that appears there. This is another free boundary, again, a boundary that you don't know. And it's not explicit, but you can mathematically say interesting stuff. In elasticity, this is another important problem. It's called the obstacle problem. What is that? You have a metal wire, and you attach an elastic membrane to the wire, and there is let's say, some obstacle, here a plane, which is below your elastic membrane. So because of gravity, your membrane tends to bend down, but there is this obstacle that doesn't allow your membrane to go too low, and then there is this region of contact, which is the region where the membrane touches the obstacle. So it's a problem in elasticity, very classical, and the goal is understanding the contact region. And this is very much connected to the problem I mentioned before of soft films. Also, it can be used to study also this problem. And another example, for instance, in porous dam, when you have some porous dam, you have water, you have filtration, and the free boundary here is the region where the dam gets wet. Another mathematical problem, where its free boundary theory enters. So this is just to say it's a very rich theory. There are many more examples, but they all fit in a single mathematical category. And the techniques are very exportable from one to the other. So this, yeah, I think it's good. Now, so Jim was really someone who inspired a lot from geometry. I mean, it's been, his research inspired a lot the geometry and problems in geometry. I personally worked many years before starting in this direction of free boundaries. I was actually working on another topic, which is called optimal transport. And I would like to briefly mention this to you, because it's a topic which actually has changed over time, and it has influenced many, many areas, and is actually now moving forward also in AI and machine learning. So optimal transport, it's a topic that started with Gaspard Monge. So you see here on the left, Gaspard Monge was a French mathematician, and he worked just before the Napoleonic era, and then also during Napoleon. And he was interested in finding the most efficient way to transport resources from one place to another. He was motivated by military applications. It was a period where the French were very active, going to be very active in the military campaign. And the idea is that, let's say, if you want to build constructions, fortifications somewhere, of course, transporting material, it's expensive, either because you have to pay for this or because just it costs workforce. And you want to do it in an efficient way, right? You want to minimize the transportation cost. So the idea is that, if I have material that I want to transport between two cities, let's say between New York and Boston, I will pay a certain amount of cost, which is usually proportional to the distance traveled between the two cities, plus how much material I'm transporting. And of course, if you just have very few possibility, very few, let's say, very few choices, it's easy to optimize. But as the complexity of the problem increases, you need a robust mathematical theory to kind of understand what's the most efficient way of transporting resources. So Monge was the first person to mathematically study this problem. Then the problem kind of got forgotten for roughly 150 years, mostly because mathematicians were busy with other topics, until Kantorovich arrived in the 1940s and kind of set all the ground and the foundation needed to solve this problem in a robust way. And even got the Nobel Prize in Economics for this work in 1975. So mathematically, this problem has been very well understood by these two mathematicians. But then, again, it remained under the radar until the 1980s. And what changed everything in the 1980s was that people start to realize that, transporting, of course, you transport is about transporting objects, but in reality, once you set up as a mathematical problem, you can transport whatever you want. It doesn't have to be a concrete quantity. So then people start to realize, I can use it in fluid mechanics. I can use it in geometry. I can use it in probability. I can use it there. I can use it there. Then suddenly, other areas of mathematics could be studied with the ideas coming from optimal transport. That's what made it very fashionable. When I got my Fields Medal, people asked me, what did I do? So this was an interpretation from an Italian comics writer that he suggested that my solution to he suggested what was my solution to go to the optimal transport problem. But actually, so there are many things you can do with optimal transport, and one of the things we did was the following: was in meteorology. So the idea is that you want to study movement of clouds, and essentially you want to understand, when you study movement of clouds, how particles move in time. Let's say you have a picture of a cloud, and you have a picture of another cloud. Just, let's say, at 2 instants of time very close by. So let's say at certain time I look at a cloud, and 1 second later I take a picture again. And clouds are made of particles, and then what you want to understand when you look at these two pictures is which point corresponds to which point. Of course, here I only drawn probably 20 points, so it's not so difficult to guess who corresponds to whom. But if I had drawn 1 billion points, or even more, because there are a lot of molecules there, it would have been a bit more complicated to understand how to match these points. So already since the 90s, it was clear that optimal transport was the right way to study this problem, because in some sense there is a points move optimally. So there is this idea in nature, right, that there is an optimality principle behind. So this was already understood. But despite having an intuition, it was very difficult to make this mathematically rigorous and robust. So it's a bit like was this discussion, right, this morning about understanding quantum field theory, what physicists understand versus what mathematicians understand. So in the 90s, Mike Cullen, a meteorologist, understood very well that this was the right way, but in some sense, the mathematics was not there. I mean, we couldn't make it work. So as a mathematician, unless you have a proof, it doesn't count. I'm sorry. I mean, that's it. And so we managed, roughly 20 years later, finally, to kind of make sense of all of this and say, no, that's really the way it works. Done. Dot, there is the theorem, no one can take that away from us. Okay, that's the good thing. So this is just one example. Another topic I worked on was the use of optimal transport in crystallography. You can use this to understand how crystals deform when you they start to deform due to, rising temperature or any kind of external force act on them. But I will not mention this today. But let's say the point was optimal transport can be used to transport objects, which is not like something we would think naturally. Here is clouds. But then people went on and they started to say, wait, but I can transport clouds. I can also transport images. So I can start to use optimal transport to do image processing, just because images are made of pixels and colored pixels, and then I can just use it to transport pixels from images. And that's where, the connection came. So optimal transport is it was used a lot at the beginning of 2010 and on. And then you see the complexity starts to become very high, because at the beginning when Monge was working about that, it was like, okay, I have a bit of material that I have to transport from New York well, he wasn't doing New York, Boston, right? He was in France, so the cities were different. But let's say I have material to transport between different cities. How many combinations you can have? But a picture is usually 1 million, 10 million pixels to 10 million pixels. You see the number of combinations start to become very, very big. And so you need some good theory to do that. But it turns out that optimal transport then became something that even the computer science community got excited about in the last few years. And a couple of examples come from this picture. So this is about the present and future now, because I think especially in machine learning, there is still a lot to be understood about the use of optimal transport. So you can use it for domain adaptation. So the idea is that maybe you study some feature in a situation like when the cities are only sunny, and then your model perhaps has difficulty to use this kind of, to recognize this feature when the cities are all rainy, right? So usually pictures have this bias where you have taken them. And so optimal transport can be used to kind of align features and make sure that your model doesn't get confused just because in one case there is sun and in the other case there is rain. Or you could use it to avoid biases. So this picture makes me think of something that happened at ETH a few years ago. So at ETH we have a lot of undergrads. So usually when I teach my students, like I'm going to do in September, I teach math and physics. I have 600 students in my class. So it's a big crowd. And we have many classes of this size. And then usually, at the end of the semester, there is the exam. And what happened a few years ago is that when we did exams, students were used to write their name and their student number on the exam. And then they will give it to the assistants who will grade them. And one year, just by chance, the coordinator of the exam forgot to say to the students that they had to write the name and said, no, you don't write the name, you just write your number. Okay, not a big deal. the number identifies the students. The only problem, or the problem that was present before, is that they realized that the moment they did that, the female students, in average, did 2% better than they were doing every time in the past out of that. Right? So you see that there is, and the number was rather big of students. So you see immediately where the bias comes from. And this is something that is very transparent. All the assistants overgrading were male, most likely also white. So they recognize names which resonate to them, and they tend to be nicer in grading when they see names which are either female names or sometimes maybe, more foreigners' names compared to the standard population. And that was kind of very transparent by looking at the few exams where this happened. And since then, at ETH, we stopped writing names. So now the exams are all graded anonymously, so you only have the code. But this is an example. So you see, you can have a bias. You can kind of recognize a bias because you see, oh, wait, there are two distributions. And there is like just a shift that doesn't make sense. And so you can try to use unilateral transport to match and say, no, we need to renormalize because there is a bias. OK, in that case, it was easy. We could just fix it by removing the name. In other case, you can try to do it with optimal transport to kind of restore fairness whenever that's possible. OK, I think my time is over, but I'm also done. So it's perfect timing. So I think what I hope I conveyed a bit is that there are many things that you can discover with mathematics, and this is what I think is the power of abstraction in mathematics. And again, I'm very, very honored to be here, and thank you, Jim, for everything you have done for us. Thank you.